All right, welcome everybody. Thanks for coming out today. My name's Nate Slater. I'm a senior manager in the AWS Solutions Architecture team. I work in the San Francisco Bay Area. We're lucky enough to have one of our premier customers in the Bay Area, Instacart, joining us today to talk about how they've been able to use the Amazon ECS service in their environment. We're going to be talking about running microservices on Amazon ECS. And with that, I'll jump right in. So today we're going to talk about a few things. First, we'll review microservices, and we'll talk about how it differs from monolithic architectures. We'll examine some of the challenges in running these microservices at scale. So one of the things you'll notice when you're running lots of different services is that as you begin to scale them out, it literally becomes impossible to do things manually. We'll talk a little bit about how you can run these microservices on ECS, and then we'll explore the Instacart use case. So let's jump into an overview of microservices architecture. So this is a definition in Wikipedia, I think it is, about what a microservice actually is. And I'm not going to read this whole thing, but the key terms in this particular document are small, independent, and decoupled. Right? A microservice needs to be those three things. And if we look at the difference between these three architectural styles, monolithic, SOA, or microservices, you'll see as we move from monolithic towards microservices, the services themselves become more and more fine-grained. And one of the things that I like to point out in this particular slide is that people ask a lot about what's the difference between SOA and microservices, and there's a lot of overlap between the two, and in many ways I feel like microservices are really just a natural evolution of SOA. If you look at the SOA diagram in the middle there, you're still going to have service boundaries with SOA. So whether you're dealing with microservices or SOA, one of the first things that you're going to really need to identify is what are the service boundaries or domains that exist in my business, and which services belong in those domains. The difference is that on the microservice side, the services themselves are smaller and more coarse-grained. Another big difference between SOA and microservices, and this is something I encountered in my past life as a career software engineer, was SOA tends to rely heavily on middleware. So SOA will oftentimes have some kind of enterprise service bus involved, and while it does a nice job decomposing the monolith into coarser-grained services, or rather finer-grained services, oftentimes what happens is that the middleware itself kind of becomes the monolith, right? You end up with a lot of business logic around how messages are being routed, business rules engines, and other things. And that's a key difference between SOA and microservices. Microservices, you have queuing, and you have asynchronous processing, and you have patterns like pub/sub, but you don't really have a ton of logic. Those are really just transport mechanisms. They're not actually applying logic to the routing of messages between services. So a monolithic architecture, everything exists in a single unit, right? So in this case, we're looking at probably some kind of CRM or ERP application where you have an order UI, a user UI, and shipping UI. Those UIs are backed by services, and those services talk to a data access component. And in this monolithic architecture, what happens is that if you need to scale this, you've got to scale the monolithic unit, right? So even if it's just the user UI, for example, that is under high load, and it would make sense, right? Maybe your user UI involves a mobile app, and you're going to have potentially tens of thousands, maybe even hundreds of thousands of clients accessing that portion of the application. The other pieces like the shipping UI and others may be much smaller, maybe even internal use only. Problem is you have to scale the entire app, right? So you got to stamp out one copy of the whole monolith. And the development cycle looks like this, right? You've got a bunch of developers over on the left-hand side there, and they're working on this big monolithic app. So they're all committing their changes into possibly like a single code repository. And then you've got to do a build when you're ready to do a deployment either for testing or for even production. You've got to go through testing, and then you've got to do a release. And this is very complicated, right? You've got all these developers that are making all these changes, so you have a lot of just trickiness around merging your code and managing the code itself. The builds themselves can be time-consuming and expensive. Testing, obviously, is difficult because even if you're trying to localize your changes as much as possible, you probably have regression risk that you're introducing into the application in areas that you're not sure of or not positive about. And then finally, you have this release, and it's usually like a big bang kind of release, right? You've got to take downtime. You have engineers coming in on a Saturday to do it. The systems are offline for 5 or 6 hours, right? Not really the optimal way of actually doing things. So in a microservices architecture, we actually decompose these services into individual units, right? So we have the same exact services and UIs as we had before, but they're independent of one another. We have our order UI, user UI, shipping UI, and the associated services. And if we want to scale these, you can see, we can scale out these things independently, right? So going back to the example of the user component, maybe that needs to scale at a different rate than the others. And with a microservices architecture, you can do this. And this is a key advantage of microservices. Microservice development cycle looks somewhat similar in that you're going to have a whole bunch of developers. But the difference is that instead of each sort of this development team all checking their code into a single monolithic repository, they're going to be working on lots of different services. And each of those services can have their own versioning, their own code repos, and the amount of code in each service is presumably a lot smaller than the monolith itself. What this means, of course, is that now you're going to have to do your build and deployment pipeline individually across all of these services, right? So chances are you're not going to wait to deploy service A until service B is ready, right? If you're doing that, then you're going to take a long time to get builds out if you have to wait for all the dependencies to be complete. So what you would do is you would actually deploy things independently. So these 6 characteristics of microservices are important. We have decentralized, right? This basically means there's no sort of monolithic central processing brain-like service that does everything, right? They're independent from one another. They're black box. Black box means that when service A calls service B, really they speak whatever language that you've chosen. Maybe it's REST, maybe it's a protocol buffer, and that's all they know about one another. They just know about that public interface. They don't know about the guts of the service. They don't share libraries, right? They don't share databases even. Polyglot, this is something that we haven't mentioned yet, but it's a powerful advantage of microservices in that oftentimes you may find that one programming language is better than another for a certain type of task, right? Maybe if you're doing number crunching, Python might be the right choice. But if you're doing something that's UI-driven, Node.js may be better. And because these services are independent and because they're their own independent code lines, versioned separately, built separately, deployed separately, you can actually now use the language that's right for the service. You certainly don't want to use lots of different languages for the sake of using lots of different languages. And we do see customers that have standardized on certain languages for microservice development, but the option is there to be polyglot if you need to. Do one thing well, right? Again, your service should be very specific and constrained in what it's actually doing, right? It should not have side effects. If it's doing authorization, for example, it should not also be updating user profile information, right? It should just be handling the authorization component. And then finally, this is something we really take to heart at Amazon, which is you build it, you run it, right? So gone are the days of having a separate QA team and separate ops teams where you lob your code over to QA and then they lob it over to ops. Really, when you're doing microservices, you are going to be responsible for the whole development lifecycle, everything from the architecture through the coding, through the testing, and then through the operational pieces of it, which today we really talk about as DevOps. Okay, let's talk about some of the challenges. And as we go through this, you'll see that really the theme in all the challenges is doing things at scale. So first, resource management, right? What you're looking at here is a diagram that shows you 3 different availability zones in one of our regions and a bunch of EC2 instances. And so you can see right here, as your fleet grows, managing this by hand just becomes impossible, right? How do you know what resources are available on a given host, right? If you have a service that needs, memory, how do you know which host to put it on, right? And with a small fleet, you can maybe manage this by hand, you can maybe keep a database, but as your fleet grows, this becomes really, really challenging. Monitoring, challenging for the same way, right? You've got potentially tens, hundreds, thousands, maybe even 10,000s of individual services. So, simple questions like how do you know if a service is healthy is difficult to answer. How do you measure the performance of an individual service? And how do you troubleshoot and debug a service that may be throwing some errors? Service discovery. So service discovery is basically how one service learns about another. It's unlikely that you're going to have a microservices architecture where each service basically does everything it needs to do and never has to call other services, right? So if service A needs to talk to service B, how does it know where service B is? And in particular, how does it know where service B is if services are scaling up and down independently from one another? Load balancers can help with this, but still, it's not the end solution. And then finally, when a service comes online, how does it announce itself to the world saying, hey, I'm available, I'm here, I can take requests? Deployment, same problem really as the other three challenges, right? We've got tens, hundreds, thousands, tens of thousands of services. Each one is being developed by a team of developers. They're all going to have their own timelines for when they develop and test and push these out. How are you going to manage this, right? Maybe you have different programming languages that you're using, so you've got different build scripts that need to run. And then finally, once you're able to actually accomplish a build, how do you decide which host to put the service on, right? Okay, so let's introduce Amazon ECS. Amazon ECS is a fully managed Elastic service, so you don't actually need to run anything. ECS will scale with your microservices architecture, right? It's got something called shared state optimistic scheduling, and there's some interesting research around different scheduling types for containers, and shared state optimistic scheduling is one of the more efficient, is one of the key attributes there. It has a fully ACID compliant resource and state management component to it. This is important, right? In a distributed system, oftentimes databases are going to have eventual consistency in them, but with a cluster of resources, you really want to have an up-to-date view of what's available in the cluster at all times without having to worry about consistency issues. And so ECS state management and resource management is ACID compliant. We've got integration with CloudWatch. So if you're used to using CloudWatch already for monitoring EC2 instances and all the other services that we support in CloudWatch, ECS has a familiar integration. And then finally, you can integrate with the CodeStar services. So those are things like code commit, code deploy, code pipeline. You can do CI/CD through those services to ECS. So let's look at what the ECS architecture consists of. So this diagram here, this architecture diagram, shows you really two different sides to the architecture. On the VPC container side, that's what you as the customer run, right? That's your VPC in your account. You've got what we call a cluster, which is really nothing more than a collection of EC2 instances that share some information about the name of the ECS cluster they belong to. That's it, right? Those container instances are nothing more than EC2 instances. They're probably running some kind of container-optimized AMI. We have the Amazon Linux AMI for ECS, for example. But other than that, they're really just EC2 instances. On the instance itself, you have the ECS agent. That's what communicates with the ECS service. And then you have your container, which has either been defined as a task or a service. And we'll talk a little bit about the difference between those two a few slides from now. So that's the customer side of this. So really, it's EC2 and VPC, right? All the stuff you're already used to using. And all the same characteristics of availability and multi-AZ and all of that apply. On the ECS side, we're providing the scheduler, and we have schedulers for tasks and services, although with the announcement about blocks today, the open source project, it looks like there's going to be the opportunity for the open source community to really contribute different types of schedulers to ECS. But today, the service itself, built into the service, is a task and a service scheduler. And then you have this resource manager. This is the ACID compliant data store and service that provides up-to-date information about the resources that are being used in your cluster at any given time. So if you're going to build an application that uses ECS, it could look like this, right? And this is a relatively simple application. You've got your ECS clusters. Those are typically going to be behind some kind of load balancer. You can use ELB or ALB. You're probably going to have DNS, right? You'll have Route 53. That's essentially providing the mapping between the ELB CNAMEs and more friendly domain names. You might use Amazon API Gateway, right? Maybe you have services that are public, right? Or they're used in a mobile application, right? And you can actually put API Gateway in front of those services and using the HTTP proxy integration with API Gateway actually have those call services that live in your ECS cluster. So, and then it's worth mentioning, you've got databases, right? You got databases like RDS, DynamoDB, Aurora, right? Your services can talk to other AWS database services. And then on the other side of the slide, you see we've got the managed service component, right? We've got Amazon ECS, that's providing the scheduling and state management of your clusters. We have Amazon ECR, right? So again, if you're pushing services out to ECS, you're almost certainly creating container images. You need to store those images someplace. ECR is a really nice way to do that. And then you have IAM integration as well, right? And the nice thing about IAM integration with ECS is that you can actually apply IAM roles down to the service or task level, right? They don't just live at the host level. So you have very fine-grained control of permissions and privileges. Monitoring with CloudWatch, we do 1-minute increments. You've got basically 4 key metrics that you're looking at: CPU reservation, memory reservation, CPU utilization, and memory utilization. And the combination of these 4 really show you essentially what's being used and what's available in your cluster. And you can break these down by cluster name or by service name, so you can see them across 2 different dimensions. Graphs and charts look a lot like, our standard CloudWatch. So these are just showing you some of the graphs that you see for these metrics. This is an architecture that shows just how the ALB service offers some interesting solutions for service discovery. And basically, if you can see here, it's a little bit small, but you can see that ALB essentially will route requests to different target groups. Target groups are hosts that are able to respond to requests of the same type, basically, that live behind the load balancer. And so you can see that in the path information, we have an auth path and we have a /weather path. And the ALB knows how to route based on that path information to the hosts behind it that are running those services. How does that help with service discovery? Well, as long as service A knows the pathing information for service B, how to construct a URL using the path information, it basically just needs to know that, and then the ALB takes responsibility for making sure it gets to the hosts that are actually running that service. So this is something where the layer 7 load balancing that we have with ALB can help. Okay, so we talked a few slides ago about the types of schedulers that we have with ECS. We had the task scheduler and the service scheduler. Task scheduler is going to run the batch jobs. These are tasks that run once, they do some work, and then they exit. You have 2 different ways that you can run these. You can do run task, which basically just randomly places it in the cluster based on the resource requirements of that task def, or you can do start task, which gives you a little bit more control over where it actually runs. For long-running apps, we call these services. These would be things like REST endpoints, for example. We have the service scheduler, and the service scheduler provides some functionality around health management, right? If you have a long-running app, you want to make sure it's up and running. You want to, if for some reason your service dies, it'd be nice to have the scheduler restart it. That's exactly what the ECS service scheduler does. It has some scale up and scale down capabilities as well. It is AZ aware, right? So if you say, hey, I need 4 copies of this service, you probably don't want all 4 of them landing on the same container instance in a single AZ. That's not really going to help you from an availability standpoint. So it'll do its best effort to try and distribute them across AZs. And then it also has a notion of grouped containers, right? So you can write a service that definition that basically says, I need an Nginx proxy and I need a Node.js Express container, and they need to be together. They depend on one another. So when you go to schedule a container, and you have a new version of your app that you're putting out or your endpoint that you're putting out, and this really should these captions are probably not quite as accurate as they should be. They should really be service 1 through service 4. You can see in step 1 we've got the green services. That's our current version, let's say, and we now want to deploy service 2. Well, what we can do is we can use these attributes, minimum healthy percent and maximum healthy percent, to say, we're okay with as few as 50% of our target services running and as many as 100%. And so what that means is that when you go to deploy your next version in step 2, you can actually take down 2 up to 2 of the existing versions, and the service scheduler will still consider it healthy, and then you can deploy the 2 new ones. And then in step 3, you eventually get rid of the old version and roll out the new one. Long-running app, this is basically just the converse of what we just talked about. Instead of decreasing the number of services, we're going to actually increase. So you can also say, well, I need 100% at minimum, but I can go as high as 200%. And so in this case, you can see we actually just in step 2 have twice as many of these running as we did in the previous step. And then finally, in step 3, we get rid of them, the extra ones, and go back to 100%. You can also do blue-green deployments, right? So standard blue-green, right? You have 2 different load balancers, maybe even 2 different ECS clusters, the blue cluster and the green cluster. You deploy to your new code to the non-production cluster, or the one that's not handling any traffic, and you can do whatever acceptance testing you need to do there. And then when you're happy with that, you can just use Route 53 weighted routing policies to essentially start to send traffic from one to another. Continuous delivery. So Jenkins, it's a tool that many customers use. If you're already using Jenkins for a non-containerized build process, really containerizing your application often is as simple as just doing the build as you normally do today, and then having a Docker file that lives in the top level of your project that essentially includes the build artifact into the container. And so the output of a containerized build process is going to be basically a container image. And once the image has been created using the Docker file in the project, you would then push that image to ECR, which is the icon at the top of the screen. And then for the continuous delivery process, you're basically going to probably have some kind of trigger that sits on top of the ECR event itself, or the push of the container to the registry, and that will trigger something a job or something that's going to then pull the container out and push it to the cluster. And we've seen examples of customers doing this where the deployment is basically you get the container and then you make a bunch of API calls to the ECS service, either calling run task or run service, telling it I want to run this. So, again, Jenkins, not a whole lot different when you're dealing with containers. Really, the key is that the final artifact from the build process is a container image, and it's that image that is used for the deployment itself. Okay, great. And with that, I will introduce Nick from Instacart, and he's going to talk about how Instacart is using ECS.
Thanks so much, Nate. I really appreciate it. So I'm Nick Elser. I'm an early engineer and now a director of engineering at Instacart. Instacart was founded in 2012 to provide delivery in as fast as 1 hour from the local grocery stores you already use and love. We're a relatively small yet nimble engineering team, and we've stayed nimble through one of our core values, which is every minute counts. And so we try to live this value, and our customers are trying to save you time. We're trying to save you minutes from going to the grocery store. But we also live that value in our engineering. We want to iterate rapidly. We want to solve for our customers as quickly as possible. So I'd like to talk to you briefly a little bit about how we leverage ECS to do just that, how we do that to iterate quickly, to solve problems quickly for our engineering team, as well as to share a little bit to make concrete some solutions to some of the problems that Nate highlighted earlier. Little background on our stack. Unlike any other startup founded in 2012, we use Ruby on Rails. However, we are a polyglot shop, as you can imagine, as we've moved into the microservices world. We've broken apart our monolith. And so for things like machine learning, for recommendations, suggested items and such, we're using Python and the data science libraries there. And for stuff like web APIs, we're using Ruby on Rails. So it's a polyglot domain. We've divided our product, our engineering platform, the Instacart product as a whole, from an engineering perspective into a few what we call domains. And each of these domains has the same SLA and is more or less responsible for a large swath. There's a huge domain of responsibility. So an example would be our catalog domain, responsible for ingesting millions of items from our retail partners every single day, adding beautiful imagery and bringing them to our storefront. Or our logistics domain, responsible for running heuristics and taking orders from our customers' domain and assigning it to a shopper that makes the most sense from an efficiency standpoint, as well as to get the order to our customers on time. So each of these domains is comprised of a few microservices, and each domain, of course, talks to each other through a service discovery mechanism that I'll talk about a little bit later. We develop in a monorepo, that is to say, all of our code is more or less effectively in one big Git repo, and this is somewhat counterintuitively allowed us to move a lot faster as a result of having really easily refactorable code between different domains, between different applications, ensuring consistency in how we do libraries and having shared libraries, and enabling all the developers are on the same page about what people are working on. And honestly, as you scale out your organization, that's helped us immensely. We develop code on a custom platform as a service. And so I'm going to talk about that now and then talk about how that helped us move from EC2 to ECS and how we leverage that to do all of the engineering effort on ECS. So the Instacart platform as a service, it's really stupid, really simple, but it works really effectively. It's basically a set of libraries and code we've written in Python that talk to two things. One is the Amazon APIs, APIs to do EC2, to do ECS, and another set of APIs to talk to our infrastructure RDS Postgres database. And essentially what we're recording in the database is changes that our developers have requested, whether that's a new deployment, a new configuration change, a size up of their fleet, whatever it is, we're recording it there, and then job systems are running in the cloud, as Nate talked about earlier, taking those requests and making them real, calling out to ECS, calling out to CloudFormation, whatever we need to do. And it's worth noting that these libraries are also running on every single developer's machine. It's rarely used for the average developer to do this directly, but allows us to bootstrap the entire fleet, the entire instances. Anything you want to run, you can run against the same APIs on your local developer environment as well as in the cloud, which means that if you're making some changes as an infrastructure team, you're using the exact same tooling that would be running on the cloud to make changes to the very systems that are running those jobs, which has been very powerful for us. So we're constantly developing against the same APIs that are making the same changes in the cloud. So why not EC2? We went through this migration over the last year, and EC2 is great. We were deploying to a fleet of services over code deploy, and things were pretty good. However, again, going back to our core value that every minute counts, it was a little too slow for us. You kind of have to make a choice when you're doing EC2 deployments to EC2 via code deploy, and that's whether or not you want true blue-green deployments, in which case you have to wait for a new fleet of instances to boot up, or you want to do rolling deploys, which is faster because you're using existing instances, but it means it could fail halfway through, and then you have to roll back or use some process there. And we didn't really want to have to make that choice. We wanted to have the best of both worlds, and ECS allows us to do that, and I'll talk about that. And that relates to the fact that these deployments are not atomic. They could fail halfway through, and that's not a great situation for some of our services. And as a final note, as a smaller note, you are constrained, but worth noting is that you're constrained to EC2 instance sizes when deploying your application, which means that oftentimes your application will be underutilized or overutilized across the various use cases. Obviously, Amazon is adding new instance types all the time, and there are various times when you need that whole instance or you want a specialized instance, so we still support doing deployments to EC2 through our APIs. But it's worth noting that it's really nice to have your application developer say, hey, I need this application to just needs 500 megabytes and 512 megabytes of RAM and one core. We don't need, but I also want a lot of bandwidth. And the ECS allows you to do that by virtue of deploying those to containers on larger machines that have access to that high bandwidth and block storage or whatever they need. So we migrated from EC2 to ECS. It was actually a relatively painless process, and we tried to make it even more painless for our developers by kind of cheating a little bit. And that's to make them completely transparent to the developer and the engineer at our company, whether or not it's a container or an instance. And we did this by, as Nate mentioned earlier, the ECS fleet is just normal EC2 instances. What we did was we attached static IPs to them, made our own DNS routing by virtue of the fact that we know where those containers are from the ECS metadata, and gave essentially, using IP tables and the DNS entry, gave each container its own DNS entry, allowing developers to SSH into them, and we treat them more or less exactly like a normal virtual machine. Whether that's best practices for Docker or not, I'm not going to tell you that's the case, but it's been really productive and really great for us to iterate quickly, especially as we evolved from EC2 to ECS. So, deployment. As I mentioned, we've got a set of jobs. When deploys are triggered, and I'll talk about how we trigger those deploys, whether through a developer pushing to a sandbox instance or our continuous delivery pipeline, it's atomic. We get the best of both worlds. You can essentially request a big number of instances as you want. They're thrown onto our ECS fleet as fresh instances, so we have the blue-green system going. And the old instances are running alongside them. So it's really, really fast as a result of using ECS. Throwing an image on to ECS is a matter of seconds, at most minutes, compared to creating a new fleet of EC2 instances. I'll talk a little bit later about how this makes our rollbacks instant, enables a lot of things there. Of course, this is possible with EC2 as well, but the primary driver for all of this was to make those initial deploys as fast as possible, that our developers are never blocked, especially when pushing out to sandbox and staging. We can do custom policies for culling old nodes depending on the workload and the type of the application. So this could be, a batch processing job. Maybe we can cull it at any time if we want to have placement for our front-end web servers, or maybe we want to keep multiple copies of our front-end web services running. We want to garbage collect them very rarely to allow us to roll back to maybe one or maybe two revisions ago, which is really powerful. And finally, our applications are sized correctly. Because with ECS, you can request as granular as down to the megabyte or to the core, as much of a size of an application you need, or a task or service. It's incredibly powerful and allows us to bin pack really effectively all of our applications. No longer do you have to make a trade-off between network and bandwidth and size and cores and all of the, you don't have to think about, the developer doesn't have to think about this. They just say, hey, Instacart infrastructure system, I need 2 gigabytes of memory and 2 cores. Easy. And it's enabled, because of the speed, this rapid pace of development, it's enabled continuous delivery at Instacart. So how does our deployment pipelines work? As Nate alluded to, we're using a pretty standard process. Git pushes, trigger webhooks. Our Jenkins servers pick those up, build an artifact, throw it up to the registry. And our job systems detect at the same time that a build has occurred. They'll run continuous integration on it, ensure that it's healthy and it's passing all the tests. Record all of those things into our infrastructure database. We have workers that are looking at the results of all of that. If it's all positive, all green, ready to go, we end up rolling that through ECS API calls and pipeline it out to 10% of our users. So this is for front-end services. Obviously, for back-end services, it goes to 100% all the time. And if those things are healthy, and we do that by having another job system that's continuously monitoring the metrics for that deploy, and if it trips some threshold, for which we look at primarily just 500s and latency, although we also look at errors for a few of them, just generic with our error checking system. If any of those thresholds are tripped, it will do an immediate rollback. But otherwise, it'll pipeline it out to the next 90% of users. And that's worked really well for us in ensuring that our API is always available, always healthy, and there's trust in it from the developers. They know that there's these systems looking at it, looking at the metrics. So I can't emphasize enough that if you're doing continuous delivery, especially on containers like this, that you have trust in your metrics and that you understand when your application is healthy and you have automated systems looking at that and doing those health checks for you. So we're doing blue-green deployments. As I mentioned before, we get a whole fresh set of instances out on our service when we do new deployments. And we're using the new ALBs, which allows you to kind of separate these very fine-grained target groups. So every new deploy gets a randomized port assigned to it for a specific application. And for front-end deploys, as I mentioned, we always keep one running, at least one, sometimes, again, pursuant to the garbage collection policy, sometimes more than one, available for more or less instant rollback. So basically, the API commands to ALB are like, hey, new deploy came out, switch service X to port blah, blah, blah. If a rollback needs to happen, you just go back to the old port. It's a matter of seconds. Users will never notice, hopefully. And because we're using separate ports, you can do constraints on this such that it's more efficient to roll out your nodes. So you can have two versions of the same application running on the same host instance, but also stripe those across availability zones and across different nodes for high availability. So it's both efficient as well as robust, reliable. It's fast. There's a lot of trust in it from our developers, and it works really well. Last, I'd love to talk a little bit about how we do service discovery and service communication. So luckily, or by chance, we came up with this system far before we migrated to containers. And essentially how the Instacart service communication and service discovery layer works is we have a set of independent RabbitMQ nodes. And I say independent as in these are not clustered. They're totally just separate, stateless, kind of dumb RabbitMQ nodes that we're running on EC2 directly. And every front-end service, that is, a service that's responding to customer requests or shopper requests, connects to one of these rabbits completely at random. But at the same time, our backend services, all of those responding to those requests, connect at least one instance, at least one version of that service is connected to every single one of the rabbits, which means that when we do maintenance or a failover happens or something like that, the very good client libraries that are available for AMQP mean that it'll be transparently retried to another rabbit and be routed to one of our backends. This also enables really, really easy service discovery, even between services that might be still on EC2, whether or not because they're legacy or because they need specialized resources like GPUs or block storage or whatnot. It's all done through client libraries. There's no load balancer involved. There's no external resources involved. It's all whether or not your service can connect to this RabbitMQ node. We do service discovery through queues. So it's really, when you're communicating with other services, hey, I put my message in this queue, one of the backend services will pull it out and give you a response. It's worked surprisingly performant and very, very robust. We've had very little problems with this. So again, this was kind of instrumental in allowing us to go from EC2 to ECS, is have this kind of agnostic system for how our different services communicate. As a final couple of notes, a couple of the other positive points of using this system are you can have instant registration and health checks. By virtue of your application connecting to the RabbitMQ node, you kind of know that it's reached a point in its boot phase, and of course we do some checks internal to that it's healthy. There's no external possible system checking that, making sure that it's healthy. The applications, by virtue of connecting, are healthy. And as a flip note, if it gets disconnected, if that node dies or the container is moved or whatnot, something happens, it'll be very transparently disconnected from the queue. Another endpoint will pick up that work, and it'll be, again, totally transparent to the front-end services, which has worked really well for us. Of course, the one con to that is that there's no way to remove a service other than just killing the service outright. And that's all from me. Thank you very much. I much appreciate it. If you have any other questions, I'm going to be chilling out over here. And thanks so much for your time.